Okay, welcome back. This is the last session of the day, and Lars will continue his lectures on cosmological aspects of the Swampland program. Thank you very much, Lars. Please go ahead.
Yeah, thanks, Amin. Thanks for the introduction. So today, we're continuing our exploration of sort of the relationship between some ideas about the Swampland to try to see how that can constrain cosmology. And today, the focus will really be on the Sitter space, sort of to understand sort of what are the constraints that quantum gravity and the Swampland program can put on the Sitter spaces. So yesterday, what we saw is we particularly focused on axion inflation, which is sort of a good candidate to drive a period of inflation in the early universe. But in particular, what we saw is that the Swampland seems to constrain this axion decay constant to be sub-Planckian. So this makes it difficult to realize, at least in this model, a period of large field inflation, which therefore seems to be in tension with quantum gravity. So today we'd like to take a sort of slightly a step back, a sort of focus more general on what are the constraints that the Swampland program puts on the Sitter space in general, and not necessarily a period of inflation. So maybe before we start with that, let me come back to a question that arose yesterday. So what we saw yesterday is that we had these particular gravitational instantons that could give rise to contributions to the axion potential. So one question is, what is the interpretation of this parameter C that appeared in the metric? And so I said it just appears as an integration constant, but of course it would be nice to have some more physical intuition. So in the case for C positive or C0, so those corresponding to these quark or extremal instantons, in that case, the C can be viewed as the tension of a brane that is wrapping a particular cycle. So that's, for example, how these quark instantons and these extremal instantons, how they can appear in string theory, where you have some brane wrapping an internal cycle, and then this tension of this brane, that is what this parameter C is. In the case for this wormhole solution where C was negative, in that case, it's really related to sort of the size of the wormhole throat. So that gives you some physical interpretation. Okay, having said that, let's move on to the topic of today's lecture, which is the Sitter space. So first, I would just like to introduce some sort of basic notions of the Sitter space. And what we're going to do is we sort of first will treat some classical aspects of the Sitter space, and then move slightly semi-classical, so sort of including some quantum effects on this background, and then see sort of when we take sort of these simple ingredients, see how that can already lead to very interesting results about how the Sitter space could be constrained in quantum gravity. So sort of one thing to note is that the Sitter space, it's a maximally symmetric spacetime with a positive cosmological constant. So on the level of the Einstein equations, it's a solution to the following equation. So we have the Einstein tensor, then we have a positive cosmological constant, and it's a vacuum solution. So the stress tensor is 0. So now when you want to solve this equation, one sort of metric that solves this and that describes the Sitter space is the so-called static metric. And this will be important later. So in the static metric, what happens is that the metric looks as follows. Sort of, it takes a similar form as for example, a structured black hole. So we have this function f of r that's appearing in front of the dt squared and the dr squared coordinates. And then we have the round metric of a d minus 2 sphere here. And this function f of r, it's given by the following. So this already looks quite similar to the metric of, let's say, a structured black hole. And so in particular, what we notice is that there the GTT component of the metric that vanishes at r equals L. So this is similarly to as the structured metric. This defines a horizon. So there's a coordinate singularity at that location. So we typically refer to this as the cosmological horizon. However, what we'll see also later, the nature of this cosmological horizon is quite different from the one that appears in a black hole. Okay, so when we draw the Penrose diagram of the Sitter space, it looks as follows. So it's a square where these diagonal lines indicate the horizon, and then sort of this static metric that we wrote down here, that only covers a quarter of the Penrose diagram. Particular, we can define it to cover this particular sort of triangle, which we refer to as the static patch. And then what happens there is a similar region on the other side here. So this is sort of a second static patch. And in this case, the cosmological horizons, as I said, they are located here. So one way to think about this static patch region, so maybe it's good to mention that r equals 0 is located here, so it's the vertical line. And then if we have an observer that is located at, let's say, this sort of the origin of the static patch, so r equals 0, that observer will be surrounded by this cosmological horizon. And then sort of the shaded static patch region is the region that is the maximal region that is in causal contact with this static observer. Okay, of course, it would also be nice to have coordinates that cover the global Penrose diagram. So we can do that and introduce coordinates that give this global cover. So in those coordinates, the matrix looks as follows. So we have sort of a global time coordinate tau. And then we have, of course, tau appearing. And then now there's the round metric of a d-1 sphere that appears here. So in particular, what that means is that when we look at a particular time slice, let's say that we're looking at the geometry at tau equals 0, then the de Sitter geometry looks like a sphere. Right, as follows. This is a tau equals 0 slice, and what's happening here, we can define 2 points on this sphere, which we can call the North Pole and the South Pole of the sphere. You can see there are sort of you can always select two antipolar points this way, and then by selecting two such points, you're sort of defining what you mean by these regions r equals 0 here. So this would be the North Pole, and this would be the South Pole. And you already see from this picture of the sphere, I can take sort of two different antipodal points. And then what that means is that I would select two different static patches. So said differently, if I look at sort of the isometry group of the Sitter space, there are isometries that do not leave the static patch invariant. So for d-dimensional, the Sitter space, indeed the isometry group is the following. So it's SO1, D, which you might recognize as the Lorentz group in d+1 dimensions. The reason why that happens is that one way how we can also describe the Sitter space is by using so-called embedding coordinates. So what that means is that we're describing the Sitter embedded in an space that is one dimension higher. And in that case, the Lorentz group in that space naturally appears. So one important aspect of the fact that this geometry of these time slices of the Sitter space are spheres is also that there's no natural notion of spatial infinity. So this should be contrasted, for example, with what happens in anti-de Sitter space, where we have asymptotic boundaries at spatial infinity, or maybe in flat space we sort of have null boundaries. So one consequence of the fact that this is not the case in the Sitter space, it's already quite difficult to sort of understand how we should define asymptotic observables. So for example, in ADS, what we can do is we can go to the boundary, and then if we use things like holography, we can define what we mean by the ADS bulk in terms of CFT correlation functions. In the de Sitter space, that's already quite tricky because there's no natural way how you can go to spatial infinity where gravity becomes weak. So that will have important consequences later on. So let's look in a bit more detail at the isometry group. And let's say that for simplicity, we're looking at three-dimensional de Sitter space. So then we're looking at SO1, 3. Then the generators of this group consist of 3 boosts and 3 rotations. So as I mentioned, there are particular isometries that leave the static patch invariant, but there are also isometries that don't leave the patch static patch invariant. So in particular, we can have 1 boost selected, and let's call it H. We can also have 1 rotation, J, that leaves the static patch invariant. Okay, so when we look at sort of how these isometries, how they act on static patch, probably looks as follows. So you can imagine, you can already see sort of in these static coordinates here, that in these static coordinates, they're static because they don't explicitly depend on time. So that is basically this transformation under the boost, which in the static coordinates appears as a time translation. So in the sort of the right static patch, this would move an observer up in time, and on the other side, it would move it down. And similarly, what can happen if we look at how the rotation acts on the static patch, we can imagine that there's this observer that is located at the origin of the static patch, and that observer could be surrounded by this cosmological horizon. This is not exactly spherical, but okay. Then we can just imagine that we're rotating the horizon, and this would leave this situation invariant. So that will be the interpretation of this particular boost H and this rotation J. And of course, what happens, we still have 4 isometries remaining. So those would correspond to the other boosts and the other rotations that do not leave the static patch invariant. So we can, for example, explicitly refer to them as the boost as K1, K2, and the rotations as R1, R2. Okay, so this is sort of what I wanted to tell you about classical de Sitter space. Are there any questions about sort of the things that I told you, like the isometry group, or anything else? Okay, if not, let me continue. So now what I want to do is sort of take this classical picture and then sprinkle some semi-classical effects on top of it. And then what we'll see sort of is sort of by combining these different ingredients, in the end we'll reach an interesting conclusion about sort of the nature of the de Sitter space in quantum gravity, which I think is sort of an interesting Swampland type of constraint. Okay, so this horizon that we have at R equals L, as I said, it's sort of similar to a black hole, but it also has important differences. But one important similarity is that the de Sitter horizon has thermodynamic properties, just as a black hole has. So this was nicely shown in a paper by Gibbons and Hawking in 77, I think. I guess later is what realized that these thermodynamic properties of horizons, they are very general. They basically apply to any type of horizon in gravity. So in the de Sitter space, what happens is that this horizon has a particular temperature. It's just given by 2 pi L inverse, where L is the radius of the horizon. And we can also associate an entropy to the horizon, which is given by the area of 4 G Newton. Okay, and already this leads to sort of an interesting picture on some of the microscopics of the sitter space, because the fact that we have this horizon suggests that there's this entropy, which is finite because it's given by the area. So if you think microscopically, then you might wonder, is it the case that this entropy is equal to the logarithm of some number of microstates, where we think about this number n, sort of this number of states. And this is at least what happens for black holes, of course, because there we have by now a wide class of black holes. We can use string theory to actually compute what are the microstates that give rise to this black hole macroscopically. And famously, people have succeeded in microscopically computing the entropy and see that it matches this area law, and also later on compute corrections to that. So that gives a very good picture, a very compelling picture that sort of string theory is a very good framework in order to do this. Because I think, as far as to my knowledge, I don't think there's any other calculation that has been done that was able to match the entropy of a black hole. So then, of course, it's a very natural question to okay, I think if the recording started again, I guess I can continue. So yeah, so what happens in perturbation theory, so when we're just sort of discussing field theory on the sitter background, then there doesn't seem to be the case that there is a finite number of states. I can just sort of activate like raising operators or something to create new states. So in perturbation theory, what happens? Perturbation theory, there's no finite number of states. So in that case, n is going to infinity. So then you might wonder, isn't this a contradiction with the finite entropy? Well, that's not really the case, because perturbation theory is valid in the limit where we send G Newton divided by L, I guess to some appropriate power in general dimension to 0. But when we take this limit where perturbation theory is supposed to apply, in that limit, we also find that the entropy goes to infinity. So at least we see that sort of in perturbation theory, there's no bound on the number of states. And this is consistent with the fact that also the entropy seems to go to infinity. So that already leads us to sort of an interesting picture under the sitter entropy, is that it should really be non-perturbative effects. Should lead to finite as the sitter. And then it's, of course, sort of the name of the game to try to understand, can we go slightly away from perturbation theory and in a controlled way take into account these non-perturbative effects to see how this can lead to finite sitter entropy. Okay, so what we'll now do is we'll try to sort of analyze sort of these non-perturbative effects and see sort of how they lead to interesting constraints on the sitter space. And I think there's a question.
Yes, excuse me. So I do understand why in perturbation theory n goes to infinity.
Yeah, so if you're just thinking about sort of like quantum field theory without non-perturbative effects, then what you can just have, for example, is let's say that you have some particular vacuum state and you just, let's say, activate the raising operator. Then in principle, you can just keep doing this and generate an infinite amount of states. Of course, what we know what will happen in gravity is at some point, back reaction effects will become important and will sort of limit this. But if we're working sort of in this exact limit where G Newton goes to 0, then this leads to an infinite amount of states.
Yes, so is it specific to the sitter space as well?
No, this is not necessarily specific to the sitter space. So this is just, I think, a statement general about Q of T. So take, for example, the example of flat space. So in flat space, there are no horizons, so there's no natural notion that there should be a bound on the number of states. And why is that the case? Because we can do this, and because flat space is sort of infinite, we can sort of spread out these states without leading to a large back reaction effect. So in that case, there is no natural way why there should be a constraint on the number of states that you can create.
Yes, sorry, I meant, is this correct about two-seater space, and is this into the real reason?
So sorry, I couldn't quite hear that.
Is perturbation theory telling us that the entropy of two-seater space should be infinite?
Not necessarily. I think what this interpretation tells you is that in perturbation theory, the de Sitter entropy is infinite indeed. But I think because we have this sort of Bekenstein-Hawking type of area, this suggests that by doing just perturbation theory, we're missing certain effects, which we should take into account in order to see that the entropy is finite.
Thank you. Thank you.
Yeah, thanks for the question. Okay. So let's say that we're looking at, now we want to do some semi-classical physics. And let's say that we want to look at a particular state in the Sitter space. Let's call this particular state psi. Then what happens is that physical states should be invariant under the de Sitter isometry group. So what that means is that if you act with one of these generators on psi, that should annihilate the state. In this case, this G are basically the generators of the isometry group. Okay, so what we'll now show is that having these generators acting on de Sitter invariant states is incompatible with having a finite n, and in particular with having a discrete spectrum of sort of energy eigenstates. So this leads to a puzzle that we need to interpret. Okay. We just write it down, so it will show. Incompatible with a finite number of states, and in particular with a discrete spectrum. So the argument was given in a very nice paper from a while back. We go here, Kleben and Suskind. In 2003. Okay, so the argument goes as follows. So let's say that we're looking at a particular sort of generator L, which is defined to be sort of this combination of this J isometry generator and K2, which was one of these particular boosts. And then if you look at the algebra, so I didn't write it down for you, but if you look at the algebra of these different generators, what you can find is that this L obeys the following commutation relation. So when you look at the commutator with this boost generator H, it is given by I times L. Okay, so what we now can do is we can now define, going from this algebra to the group element, so we can define the following group element. E to the IL. And then we can try to look how this group element, how that evolves under time evolution. So what you can do is we can evolve with a time evolution operator. I guess it's important to remember that this H, this boost generator, generates time evolution in the static patch. So then try doing the following. Okay, what we'll now do is we'll slightly rewrite this time evolved group element using the Baker-Campbell-Hausdorff formula. So if you're not familiar with that formula, don't worry too much. I'll just show you what it tells you in a particular case. There's a nice Wikipedia entry on it if you're interested. So what this Baker-Campbell-Hausdorff formula tells you is, let's say that you have a commutator of the following form of some x and y, proportional to some number s times y. Then what happens if we look at this e to the x, e to the y, e to the minus x, then this can be written in the following way. Okay, so when we apply this formula to our time evolved e to the il, what we can do is we can rewrite it as follows. We just pick up a factor of e to the minus t. Okay, so now what we can do is we can try to look at the absolute value of the expectation value where we act with this particular operator on this particular state psi that we're interested in. So first we can just look at the expectation value without doing time evolution. So then we would get the following. So then this psi is not necessarily an eigenstate of this e to the il, but if you go to a basis and look at the eigenstates, what you can show is that because e to the il is a unitary operator, what happens is that you will get, you can write this as 1 minus delta. Very importantly, delta is positive. So definitely it's always possible to find a particular state psi for which this is true, where delta is positive. Okay, so this is sort of the expectation value of this e to the il, let's say at t equals 0. And then we can also consider what happens when we look at the time evolved expectation value. Now what we do is compute the following. And then using our result from this Baker-Campbell-Hausdorff formula, we know that we can write it in the following way. Okay, so what does that now imply? So we see we sort of have two expectation values of interest. Let's say that we take the limit of t going to infinity of this expectation value f of t. So by doing that in this expectation value here, what we see happening is that this goes to 1. However, what we also know is that when we look at sort of f evaluated at t equals 0, we can use this result. We can use this result. Then we find that this is smaller than 1. So you might wonder, why is this relevant? So what we'll see in a moment is that sort of these properties, when we impose that we have a discrete spectrum of energy eigenstates, this will be incompatible with these other isometries. Okay. But before that we can show that, we need to use a little bit of sort of math results. So what does math tell you? It tells you, let's say that you have a function of the following form. So you have some sum over n, some coefficients fn, and then there is sort of this I omega n t appearing. So later we can think of these omegas as energies over state, but this is just a general result about these functions. So then we have a function of this form. This function is quasi-periodic. It's quasi-periodic when these coefficients obey the following bound. So they just should be bounded by infinity. You can sort of see how this. So what we mean by quasi-periodic, sort of the definition is a little bit fake. but for us, it's sort of enough to understand. We see this particular periodicity of this exponential function appearing, but then it's sort of modified by particular coefficients that multiply it in front of it. But importantly, what we should just have in mind is that we can have this function that is sort of oscillating, but there can be these little coefficients in front of it and make it not exactly periodic, but quasi-periodic. However, what's important is, let's say that this function f of t, if this is quasi-periodic, maybe I should say, so if f of t is quasi-periodic, what it implies is that this is incompatible with this property that the limit exists and goes to 1. So why is this the case? So you can try to prove it in a more formal way, but sort of intuitively what happens is that what we're having is sort of this oscillating function. So a simple oscillating function, you can think about it like as the cosine. So when we take this limit where t is going to infinity, that does not have a well-defined limit because it just keeps oscillating. So similarly, this is also the case for these quasi-periodic functions, that if you have such a quasi-periodic function, this limit where t is going to infinity and we get a finite value should not exist. So if we can show that this function f of t is quasi-periodic, this is incompatible with this existence of this function f of t, and in particular these de Sitter symmetries. And what we'll now show is that that's indeed the case, and we'll give a particular interpretation of that, what it implies for the de Sitter symmetries. Okay, so what we now will assume is that the state psi that we're looking at has a discrete spectrum of energy eigenstates. So if that's the case, then we can write this function f of t as follows. So we now expand this in energy eigenstate. So we have some particular coefficients fn star fm e to the il m times e to the I omega n minus omega m t. Okay, so when we do this expansion in energy eigenstates, what we see is this function f of t. It looks pretty similar to our definition of a quasi-periodic function, which I guess the only difference is the fact that here we sort of have 2 omegas appearing, and here we have just 1 omega appearing. So in order to do this properly, you can also look at a quasi-periodic function where you have these 2 omegas and these 2 coefficients. And then we can still use the result that this function is quasi-periodic when these coefficients are bounded. So in particular, if this function f of t expanded in this energy eigenbasis, if that is quasi-periodic, what we need to show is the following. So we basically sort of take the square of these coefficients that are appearing in front of this exponential. So what we want to show is that the following is true. So that these coefficients, this is bounded by infinity. And if that's the case, then this function f of t is quasi-periodic. So how can we do that? Well, we can just start with we can start with 1 and write it sort of as the overlap state. And then we can write it in the following way. So here what we're doing is we're just inserting a complete basis of states in order to rewrite 1 in a nice way. where we make use of this e to the I. Okay, so then now if we make use of the fact that these coefficients that were appearing in the expansion of the energy eigenstates, that these are bounded. Which is, I guess, a general effect of life. And when we're looking at normalized states, then it follows that the following coefficients are bounded. Now, we look at this particular result here. With this particular result here, and we just multiply by these coefficients, and then we can derive the following inequality. So now what we see is that this should be smaller or equal than 1. But what's important now is that what we see is that these particular coefficients are bounded. This is precisely what we're aiming to show, that this is bounded by infinity. So our conclusion is that if we can do this expansion of f of t in terms of energy eigenstates, what we find is that f of t must be quasi-periodic. Which is in violation with the property star, which was the fact that this limit of t going to infinity goes to 1. Okay, so this is quite it's quite technical, and you might wonder, what does this mean? So what this means is that what did we start out with? Well, we started out with assuming the de Sitter isometries, and then we assumed that we could that we had the discrete spectrum of energy eigenstates, which seems to be compatible with the fact that we also have a finite n or a finite entropy. But then the conclusion that we arrive at is that the isometries of de Sitter are incompatible with a finite entropy, or maybe more precise, with a discrete spectrum of energy eigenstates. Okay, so this is quite important because you might be saying that, okay, I'm interested in sort of studying quantum gravity in the Sitter space. But what I find in the end is that these isometries are incompatible with finite entropy. So what is the interpretation of this? Well, typically the interpretation is that we know that in perturbation theory, the de Sitter isometries don't tend to break down. And again, this is compatible with the fact that in perturbation theory, n is going to infinity, and we don't expect this discrete spectrum of energy eigenstates or having a finite entropy. So what it suggests? What it suggests is that non-perturbative effects result in a finite entropy, which we already argued for. Finite entropy, a discrete spectrum of energy eigenstates, plus what we can now argue for is a breakdown of the de Sitter isometries. So what we have in mind is a situation where in perturbation theory, we can have this de Sitter isometries that are exactly realized, And that is not incompatible with having this finite entropy. But at the moment that we're also interested in studying some non-perturbative effects, then the entropy becomes finite. And then we run into this problem that we get this incompatibility with the de Sitter isometries. So you might expect that there's a breakdown of the de Sitter isometries at some particular energy scale where these non-perturbative effects become important. And a very conservative estimate of this particular time scale is that it should scale with the de Sitter entropy exponentially. And the reason for this is, for example, one non-perturbative effect that you could imagine that breaks the de Sitter isometries is, for example, the nucleation of a black hole. What we saw is that in the de Sitter space, there's this thermal spectrum. So we're in a thermal situation. So that means that eventually, if you wait long enough, sort of rare fluctuations will occur. So if you nucleate a black hole, for example, this will break the de Sitter isometries, in the sense that having this black hole, there are some of the isometries that are no longer preserved. So what you could imagine is that sort of if you start out with pure de Sitter space, if you wait sufficiently long enough, this will be the end of the type of experiment that you can do by performing measurements. So this would be sort of an extremely conservative sort of swampland bound on the lifetime of de Sitter space. But of course, it's an interesting question to understand if such a breakdown of the de Sitter space could already happen at an earlier time scale. So that, I guess, sort of motivates us to try to understand more generally the constraints that the swampland puts on the de Sitter space. But I think this is sort of the zeroth order constraint that is very important. And maybe I should stop for questions about this derivation because it's a little bit technical. So feel free to ask me about it.
Excuse me. So I guess there was a typo in the pages ago. But I mean, that e above power IL of t was something. I mean, I guess the second L was supposed to be H, right?
Sorry, where are you referring to?
A little bit before that.
Somewhere here.
It's the Heisenberg picture transformation. So it was, I mean, before. Sorry, I should have mentioned already.
No, it's okay.
Okay, here. Yeah.
Yeah, sorry. I see what you mean. Yeah, indeed. Sorry. It should be e to the, oops. It should be e to the minus ht. That was what you were worried about, right?
Yes, thank you. Sorry.
Okay, yeah, good. Thanks for.
And there was another question. I was wondering, I don't know if I have to wait until the end of the lecture, but is it correct to interpret the de Sitter entropy as the entropy of what's outside the horizon, beyond the horizon, beyond the de Sitter horizon?
Yeah, I think that's a fair way of seeing the de Sitter entropy indeed. So one way, and this is, I think, something that we'll see tomorrow also, is one way to think about the de Sitter entropy is the following way. Let's say that we're drawing the static patch regions, and then so we have the static patch here, we have the static patch here. So then let's say that you're looking at the density matrix in this static patch, for example. So let's call that the south pole. So we can write it as, let's call it like alpha or something. This is the state that you're interested in. Then what happens is that this density matrix is thermal. And what you can do is you can sort of, you can introduce this second copy, this other static patch, to find a density matrix of the total state. So that would be, I guess, let's call that as de Sitter, where we call that psi. Then what you can do is if you look at the von Neumann entropy associated with this total state, then the von Neumann entropy is 0, because you can define the state to be pure. So by pure, that means that its von Neumann entropy is 0. But now what you can do, if you can define this density matrix that is located at one of the poles, you can define this as a trace over this total de Sitter state where we trace out the other static patch. So when you do that, you get this thermal density matrix, and you find that this has a von Neumann entropy, which is given by S de Sitter. So in that case, indeed, you can sort of view the entropy that is measured by the horizon as sort of the entanglement entropy between the two static patches. And then indeed, as you say, it's sort of the entropy that arises by sort of neglecting part of the space-time. So it sort of indeed captures the information that is beyond the horizon. So that, I think, is a very interesting interpretation.
Thank you.
Okay, so I have only 10 minutes left. So there's still something that I wanted to show you. Let's see. Okay, maybe I can briefly mention a few things about the de Sitter conjecture, and then we can end. Okay, so what we just saw is that these de Sitter isometries, they seem to be incompatible with the fact that you have finite entropy. And in particular, you can have these non-perturbative effects which break your de Sitter isometries. And the fact that sort of you have these non-perturbative effects, it also suggests that if you're performing experiments in de Sitter space, let's say that you want to measure the radiation or something like that, then at some point you will nucleate this black hole and your experiment will be destroyed. So in a more formal way, what it means is that there's no natural way of defining asymptotic observables in de Sitter space. Because there's no experiment that you can do that can last for an infinite amount or a very long amount of time, in which you become more and more precise, because at some point you will not survive this. So there's a nice perspective on the de Sitter conjecture that precisely relates to this notion of asymptotic observables, which is in a relatively recent paper by Tom Redelius. And the archive number is 2106 09026. Okay, so what's the argument of the paper? Well, perhaps you have already heard about the de Sitter conjecture in other lectures, but if not, let me briefly mention it. So the de Sitter conjecture basically tells you that if you have a potential that depends on some moduli or scalar fields, if that's derived from quantum gravity, the de Sitter conjecture suggests that at least asymptotically there should be a bound on its slope, which is given by the following. Here we are taking derivatives with respect to the different possible scalar fields. Should be bigger or equal than some particular constant C, where C is supposed to be an order 1 constant. And again, it's similar to the action V gravity conjecture. Its precise value is not completely clear, but you can try to fix it by requiring sort of the fact that you can have asymptotic observables in cosmology. So how does that work? So let's say that we have an observer in the Sitter space, or maybe more generally in a cosmological spacetime. So you can also consider inflation, for example. Then if we want to have asymptotic observables, we need to have the following criteria. We want to make sure that an observer can survive the experiment. In particular, we don't want the observer to be destroyed by a black hole at some point. There should be no bound on the entropy that this observer can harness. Because if you have a bound on the entropy, that means that sort of you have a finiteness on the precision with which you can measure observables. And I guess you want the observer to be able to harness some entropy in order to do the experiment. To like build a sufficiently complicated measurement apparatus. Okay, so then we can try to look at sort of different types of cosmological spacetimes and see if we can sort of satisfy these criteria, and then try to relay that to this constant C that appears in the de Sitter conjecture. So let's say that we define the equation of state parameter as follows. Omega is the pressure divided by the energy density, which is, I think we already saw this in the first lecture. And then if you have de Sitter space, for the de Sitter space, omega is -1. So it has the equation of state of a cosmological constant. So in that case, there is a bound on the entropy, which is given by the at least bounded by the entropy of the horizon. So we cannot have more entropy than that in the Sitter space. So that's not very good for our prospects of defining an asymptotic observable. And what is more, that fluctuations will destroy you eventually. Because you're in a thermal bed, if you wait long enough, and if you perform your experiment long enough, then eventually what will happen is that we enucleate these black holes sort of related to destroying the Sitter isometries. Okay, so in the Sitter space, there's no good notion of an asymptotic observable. Of course, if you're thinking about smaller timescales, like in our own universe, there's no problem, but sort of in a formal way when you want to define these asymptotic observables, then there is this problem. Okay, so then we can also think about what is typically referred to as Q space, which has an equation of state bigger than -1, but smaller than -1/3. And we can roughly think about this, or maybe exactly think about this as inflation, because this is precisely the equation of state that you need in order to generate an inflationary period. In that case, what happens? This space-time still has horizons, but what's happening, because the Hubble parameter is slowly decreasing, these horizons grow. So we can, for example, look at the apparent horizon, which is basically just the inverse of the Hubble parameter. And when we express it in terms of the equation of state, we find the following. In particular, if we take t to be very large, we find that the apparent horizon grows to infinity. So what that means is that there's no bound on the entropy asymptotically. So that's good. And then we think about the temperature, that is also decreasing because the horizon is increasing. So we can still approximate it by h/2π. And then in terms of the equation of state, it takes the following form. So again, we see that if we're looking asymptotically, then there are no, because the temperature goes to 0, there are no deadly fluctuations asymptotically. So in Q space, the prospects of defining an asymptotic observable are much better. There's no, in principle, there's no bound on the entropy, and there are no deadly fluctuations that eventually will destroy it. However, let's say that we want to do some complicated measurement and build a highly complex measurement apparatus. And what we want to do is we want to have a system with sufficiently large entropy. So what that requires is we need to harvest the entropy in Q space. And the only source of sort of these high entropy fluctuations would be these thermal fluctuations, which might or might not be possible. In particular, this will be quite tricky if you think about later times, because the typical wavelength of these fluctuations becomes larger and larger, so they're sort of more and more redshifted. So then, in practice, this might be impossible. And this depends a little bit on your perspective of what an asymptotic observable should be. So in sort of for now, the point of view that we're taking is that this is not a nice way of defining an asymptotic observable if you need to harness these sort of very long wavelength fluctuations. This is difficult for the asymptotic observables. Okay, and finally, the situation that we can consider of a cosmological spacetime is a decelerating universe. So that would correspond to having an equation of state that looks as follows. So that has omega smaller than 1 and bigger than -1/3. So for example, I guess radiation or matter domination in our universe would correspond to a decelerating universe. So in these type of spacetime, there's no horizon anymore. So in particular, what that means is there's no bound on the entropy, no bound on S. There are no fluctuations. Can destroy you. And also, there's no way that we're constrained by building a complicated measurement apparatus because there's no horizon. We basically have the entire universe at our disposal to build a complex measurement apparatus. So if you want to have a nice definition of asymptotic observables, this seems like a good situation. Okay, so now we see these sort of 3 different spacetimes. So what I told you in the beginning is that we want to relate sort of the presence of these asymptotic observables to the de Sitter conjecture. So how this is related to the value of C. So what happens if we want to preserve the de Sitter conjecture under dimensional reduction? This is sort of a principle that has been applied more often in the Swampland program. Then what you find, at least in 4 dimensions, is that the value of C that appears in the de Sitter conjecture should be square root of 2. So now let's see how that relates to this presence of these or absence of the asymptotic observables. So let's say that we're considering a potential of the following form, which is a typical potential that you find asymptotically in moduli space when we're looking at, for example, flux compactifications. Then what the, let's see. So then what the de Sitter conjecture tells you is when we look at, take a value of C equals to 2, square root of 2, then the de Sitter conjecture tells you the following in terms of this potential. Tells you that L should be bigger or equal than square root of 2. So how does this relate to the asymptotic observables? Well, what we can look at is we can look at the equation of state for this particular exponential potential. And what you find for the equation of state is the following result. You find that omega is equal to -1 plus lambda squared over 3. Okay, so translating the value of the de Sitter conjecture, lambda should be bigger or equal than square root of 2 to omega. What we find is that, according to this conjecture, that omega should be bigger or equal than square root of, bigger or equal than -1/3, which, as we just saw, corresponds to the boundary where we are looking at the decelerating universe. Okay, so what this suggests is sort of this notion of having an asymptotic observables, this breaking of the de Sitter isometries, and this de Sitter conjecture, they seem to be very closely related. In particular, so what we saw is the de Sitter isometries cannot be preserved non-perturbatively. There are particular effects that break it. And sort of this breaking of the de Sitter isometries and the fact that you can have these fluctuations, that also seems to preclude the existence of asymptotic observables in de Sitter space. And if you try to go to Q space, the situation is slightly better, but still not perfect. You really need to have sort of this notion of a decelerating universe in order to define what we mean by an asymptotic observable. So if we take that sort of as our ingredient, we see that this precise value where we have a decelerating universe precisely is compatible with the de Sitter conjecture. So what does that mean? So I think a reasonable interpretation to have for this type of phenomena is the fact that these type of Swampland conjectures, and in particular the de Sitter conjecture, is only supposed to hold really asymptotically sort of in your moduli space. So what you could happen is you could still have at least some period of inflation sort of, I guess, perhaps in the bulk of moduli space, but perhaps what should happen at some point is that if you go to sufficiently long times, should sort of transition to a universe where that is decelerating. So in terms of the Penrose diagram, what we can imagine is that we do something as follows. We have a phase of the Sitter universe, but eventually we want to end that phase and glue to a decelerating universe. So what you could have here is a Sitter phase. And at some point, we want this to be related to a decelerating universe. In order to be able to properly define these asymptotic observables. And clearly what this means is that the Sitter space does not seem to be supported eternally, but only for a finite amount of time. And I guess it's still sort of a topic of debate precisely what this bound on the timescale is. But all these arguments seem to point to the fact that the Sitter space is not something that can last eternally. And that brings me to the end of today's lecture. So what I would like to tell you tomorrow in the last lecture is sort of more modern developments of what people have considered in order to try to sort of understand these particular non-perturbative effects, sort of what could they precisely be, and sort of see how that relates to the finiteness of the entropy in the Sitter space. So let me end there, and if there's still some questions, feel free to ask me. I think I can't hear you. I mean, I think your microphone is on, but I hear you very softly.
Is it fine now?
Yeah, I now hear you. Yeah.
Okay. Thank you very much for interesting lecture. We have time for questions, please.
Hi.
Matthew, yeah.
Question.
Yeah, please.
I didn't quite get why those fluctuations are disturbing or deadly, as you said. So you mean quantum fluctuations exactly?
Yeah, so I guess there's sort of two ways of viewing it. So one way, if you think about it from a static patch perspective, what will happen is you basically have this horizon and we're attributing thermodynamic properties to it. And what happens is that because this is sort of described by a Gaussian, what you could happen at some point is that there is a particular fluctuation with high entropy that is being generated. So one example that you could have in mind is that just you sort of have this thermal system, so it's exploring its phase space. And at some point, there's a black hole that is being nucleated, which will be an example of such a high entropy fluctuation. And sort of the key about the Sitter space is that these fluctuations, they're extremely suppressed. They're e to the minus s, the entropy of that object. But eventually they will happen if you wait long enough with probability 1.
So the upshot is that the Sitter conjecture implies that, I mean, if you want to have observables, if you want to measure something, there must be this bound, at least asymptotically.
Yeah, at least if you, so, and then of course, the thing that you're putting in is that you're requiring that there is these well-defined asymptotic observables. I guess it's fair to say sort of in inflation, we're typically not too worried about it because we're not necessarily thinking about these non-perturbative effects. You're saying we have like C and B correlation functions, which are fine. But if you want to understand quantum gravity, then you really need to think about this non-perturbative effect. And then this might be an issue.
Right, thanks.
Okay, another question? Okay, I do not see any questions. So thank you very much, Lars, for the beautiful lecture. So let's join together tomorrow for the final lectures. Thank you very much.
Yeah, thanks a lot, and see you tomorrow for the final lecture indeed. Yeah, thanks.
Okay. Goodbye, everyone.
Bye-bye.